Hello, welcome to this video. Today we're going to prove this inequality. So we need to show that for all positive numbers x, y, and z that satisfy 1 over x plus 1 over y plus 1 over z equals 3 over 2, the following inequality holds. So we have x plus y plus z all to the 6th power divided by x plus yz, y plus zx, y plus dx, and z plus xy. Here, you could factor things out and try to move it around and get that some polynomial of x, y, and z is bigger than or equal than 0. But that's just going to be a nightmare since this is to the 6th power and 3 terms inside. It's going to be terrible, and factoring this is also really bad. So we're going to have to use a different approach. What we're going to use is AMGM, which is the inequality of the means of numbers. So there's the inequality that everyone knows about, or like a lot know about, like x1, x2, up until xn, that are all bigger than or equal to 0. They satisfy that the sum of them divided by n, so their algebraic mean, has to be bigger than or equal than the nth root of their product, which is their geometric mean. But there's also an extension to this inequality, which is that it's bigger than, this is also bigger than or equal than the harmonic mean, which is n divided by 1 over x1 plus 1 over x2 up until 1 over xn. And this is smaller than the it's something that I believe is called the RMS, which is something like root mean squares, root of mean of squares, or something like that, which is pretty much as it sounds. You take the square root of x1 squared plus x2 squared up until xn squared and divide it by n. So basically take the algebraic mean of the squares and do the square root. And this is like the full-on AMGM inequality, and we're going to use every single part of it. So first we're going to use the basic one. So what we're going to use here is that the product of these 3 numbers is smaller than or equal than their sum divided by 3, all cubed. So this thing, which is the cyclic product of x plus y, z, we know this is smaller than or equal of then the cyclic sum of x plus y, z divided by 3. So basically this is their algebraic mean, but then we cube it. Right? If we were to do a cube root on both sides, this would just be this inequality for 3 terms. But then after we cube both sides, we have this smaller or equal to this. But this is on the denominator, meaning that x plus y plus z to the 6th power divided by this, it's bigger than or equal, is smaller than or equal than this. So if we prove that term is bigger than or equal to 216, then we would have proved that this is bigger than or equal to 216. So this is smaller than or equal than this. So if we prove this is bigger than or equal to 216, we're done. So let's try and do that. First of all, we have a 3 cubed here, and the denominator of the denominator, we can bring it up to be a 27. So this is just going to be this thing cubed, and we multiply this by 27. So now we can move the 27 to the other side. We'll have x plus y plus z. It's the 6th power, and I'll already multiply on both sides by this number. And we get this inequality is equivalent to 216 divided by 27 is 8. So this is 8, the cyclic sum of x plus y z all cubed. So this is equivalent to if we take the cube root of both sides, which leaves us with a cyclic sum of x squared bigger than or equal than 2. So the cyclic sum of x plus y z. Alright, so cube root of this is this, cube root of 8 is 2, cube root of this is just the thing inside the cube. So now, this is much easier to factor than x plus y plus z to the 6th power. This inequality is obviously equivalent to, if I just factor this out, this is going to be the cyclic sum of x squared plus 2xy. And we need to show this is bigger than or equal than the cyclic sum. So I bring the 2 inside the sum, and we'll have 2x plus 2yz. Now, the cyclic sum of 2xy is actually the exact same as the cyclic sum of 2yz, right? This is going to be 2xy plus 2yz plus 2zx. This is going to be 2yz plus 2zx plus 2xy. The order is different, but obviously the sums themselves are the same. So I can just cancel them out, and I have now left to prove that the cyclic sum of x squared is bigger than or equal than the cyclic sum of 2x. Right? If this is true, then this is true, and this is true, this is true, this is true, and then this is true. So I know one thing, and that is that the square root of the cyclic sum of x squared divided by 3 is bigger than or equal than the cyclic sum of x divided by 3, right? This is just this inequality. So now I'm going to do something like this. I'm going to set this to be u and show that u is bigger than or equal to 2. So let's look at this. So now here we just have that this number is u. So this is obviously bigger than or equal than this number, right? Since it's bigger than or equal to geometric mean, which is bigger than or equal than harmonic mean. So this is u is bigger than or equal than 3 over the cyclic sum of 1 over x. And here we're finally going to use our given, which is that the sum of 1 over them and sum of their inverses is 3 over 2. So now this is just equal to 3 over 2. So this is 3 over 3 over 2, which is 2. So indeed u is bigger than or equal to 2. And if u is bigger than or equal to 2, that means that u is bigger than or equal than square root 2u, right? So u squared is bigger than or equal to 2u. We take the square root. These are positive numbers, so we're allowed to do that. And we get u is bigger than or equal than the square root of 2u. So this is bigger than or equal than the square root of 2u. And so, again, everything is positive here. This means that this number is bigger than or equal than this number. So the cyclic sum, so we get from here that the cyclic sum of x squared over 3 is bigger than or equal than, well, what is 2u? u we define to be sum of x over 3. This is going to be bigger than or equal than 2. So the cyclic sum of x over 3. The 3's cancel out, and indeed the sum of x squared is bigger than or equal than 2 times the cyclic sum of x. And I can obviously bring the 2 inside the sum together this is the cyclic sum of 2x. So indeed this is true, and again, right, by everything and then again we can work backwards. If this is true, we can add these to both sides, and then represent this as the sum entirely squared, then cube it, then multiply by 27 and divide by this, and then this is just smaller than or equal to this by this inequality, which again as a reminder is just AMGM straight from here, and meaning that this inequality is true. And just like as another bonus, when is inequality reached? When does this exactly equal 216? Well, for this we need to look at this. When are all of these the same number, right? And all of these are the same only, or any two of them are the same only if x1 is equal to x2, which is equal to xn. That is the only place where inequality is reached on any of these three inequalities. So this one, and this one. Meaning that on everything we said, if we want everything to be equal here, actually all of this x plus yz have to be equal, but also this like u has to be equal to 2, meaning it has to be actually equal to 2, which will make it so that this side is equal to this side, so which will mean that x and y and z are just straight up the same number. And from this we'll get that the only time where equality is reached is when all three of them are equal to the same number 2. And so finally, that's it. If you want more content like this, please subscribe to my channel. I'll be uploading more interesting problems and things like this in the future. Finally, that's it.